So you've just done your P4 test. Let's take a look at some of the answers. So first question, we have got a multiple choice. And whenever you've got a multiple choice, one of the best things that you can do is go through each of the answers first and work out which ones are likely, which ones aren't likely. So at least then you can rule some of them out straight away. So the correct answer that we should have got were this one and this one, and we need both of them to get a mark. So we need both of those right to get our mark there. Here we are, well, what we have to do is she thinks this agrees with her prediction. So we have to take a look at what her prediction is. So here's her prediction up here, and her prediction is that the work done pulling the trolley up the ramp will be equal to the change of gravitational potential energy. And we need to say, well, is she correct? And we need to justify our answer. So the way that we can justify our answer is to be doing some calculations. So we are comparing the work done. So work done is the force of something times the distance that it's travelled. Now let's take a look at our diagram. What was the force and what was the distance travelled? Well, the force up the ramp, 4.8 newtons. And when we're saying the distance, well, we're saying the distance, but it's not this distance here, because this is the vertical distance. It's not this distance here. It's this distance here up the ramp, 0.25 meters. So back down to where we did our calculation. So we have 4.8 times 0.25, and that gives us an answer of 1.2 joules. And what we're comparing the work done to the gravitational potential energy, because this is what's in Enid's prediction there. And gravitational potential energy is the weight of something times the height. So let's scroll back up. Let's see what the weight is. Well, it doesn't tell us what the weight is in our diagram, but it tells us the height. Height is 0.15. So we can put that straight in there. 0.15 for our height there. And it does tell us the weight of the trolley. It tells us here. So there's our weight. Let's pop that in here. So what we're doing 6 newtons times by the height that it's going up, and that gives us an answer of 0.9 joules there. And if we compare, the work done here was more than the gravitational potential energy change there. So was Enid's prediction correct? Well, no, it wasn't, because she predicted that the work done was the same as the gravitational potential energy. And as we can see, they're different. So we can write as well for our answer, she is wrong. And let's see what we get marks for here. So we get a mark for, first of all, we need to say if she's wrong, we get a mark there. And we get a mark for justifying it. Okay, it says justify your answer, and we've justified it by doing a calculation. Okay. So that was your first question there. Second question is one of those 6-mark questions. So what I would recommend is, instead of going through all the different possibilities, I'm just going to put the mark scheme up on the screen, and then you can pause it and then mark your script using that on the pause screen. So here's the mark scheme. Pause your screen now and mark your work. Okay, moving on to our next one. We are looking at a bulletproof vest, and the bullet comes out of the gun into our bulletproof vest material. So this here is our bulletproof vest material here. And what have we got to do? We have got some numbers here. So what have we got? We've got the mass of the bullet there. We've got the velocity of the bullet. And what's this? That's the time it takes for the bullet to slow down. And we've got a way of converting from grams to kilograms there. So they're the numbers that we've got. And we're being asked, what is the momentum change of the bullet? So we need to find the momentum change, okay? And I'm just going to start working up here for the moment. So I'm going to put, let's use black, that's better. So we're going to use, so we're going to go for momentum change. I'm just going to put that as MOM, so momentum change. And the change in momentum is the momentum before. Nope, it's not the momentum before, sorry about that. It's the momentum after. Take away the momentum before. So momentum after minus momentum before. So what's our momentum so our momentum afterwards, well, that's quite straightforward. It's gone from being moving to not moving, so our momentum afterwards is going to be 0. So we're looking for the difference between what it was at the start and what it was at the end. Okay, and what was our momentum before? Well, to calculate the momentum of something, so momentum, use that abbreviation again, well, it's the mass of something times the velocity of something. So m for mass, v for velocity there. And let's have a look. Our mass here is 15 grams, but we can't use 15 grams because when this equation only works in kilograms, so 15 grams in kilograms is 0.015 kilograms. So we need to do our mass 0.015 times that by our velocity, 420 meters per second, or 2. And that gives us an answer of 6.3, and units kilograms, meters per second there. And so the answer that we need to give, what we actually need to do, is we need to put a circle, we need to put a ring around this one. And then, well, if you've done that, then you get a mark there. We also need to calculate the force exerted on the vest as the bullet stops. So to find the force of something, we need to do the change in momentum and divide that by the time taken for the change. And our change in momentum, well, it's going from, it's 6.3, and our time is really small number here, so 3 times 10 to the minus 5, and our answer here, we should get 210,000 newtons. So 210,000 goes in there. Take a look at the next question. So Clint investigates the use of foam material in bulletproof vests. Both vests have the same weight but are much thicker. Explain how the thicker vest could be better for the wearer when it stops the bullet. So let's take a look at what answers we could have got, and there's 3 possible answers that we can have, 3 possible points that we could make, and if we've got 2 of those 3, then we get both of those marks. So first of all, we needed to, one of our options is, we need to say the bullet can travel further before it stops. So thicker vest travels further before it stops. If it travels further, second point we could say is this takes longer for it to stop, a longer time for it to stop. And the final point that we need to make is that reducing the force or that this reduces the force. So there's a reduction in force or a reduced rate of change in momentum. So there are three possibilities. Bullet can travel further, more time to stop, and reducing the force there. Next question. So this one is all about the peer review process. And there are 2 marks available for this. And we get our first mark if we identify that F is the wrong one. Okay, so where it says the publisher pays the scientist to repeat Clint's experiment, that's not part of the peer review process. So you get 1 mark if you disregard this part. So if you ignore that, then you get 1 mark there. And the bit order that we should have got is A, C, E, B, and then D. And the person who's giving the good scientific freedom for not publishing the work is Bess. Next question. In this question, we're looking at 3 different electric cars, and we are being asked, so the manufacturers of Go Far claim that their car has the greatest acceleration. Are they right? So we need to compare the acceleration, okay? And let's just make a note up here that the acceleration is equal to the change in V for velocity, change in velocity, times, no, not times, divided by time taken. So change in velocity divided by time taken. Okay, so let's just straighten this out. Change in velocity times, done it again. In fact, let's put our in fact, let's start again. I messed this bit up a little bit. The acceleration is the change in velocity divided by the time taken. So we need to get the full justification here, we need to compare the velocities. So let's take a look at what our velocities are. Let's take a look at City Stroll first. Their change in velocity is 25 meters per second. So change in velocity from a 0 start, so from 0 meters per second when it's not moving to 25 meters per second, it takes 10 seconds. So 25 divided by 10. Our City Stroll car has got an acceleration of 2.5 meters per second squared. Let's take a look at our next one. So our Easy Shop, that has a change of speed of 15 divided by the time that it takes to accelerate, 5 seconds, and that means it's got an acceleration of 5 meters per second squared. Take a look at our final one, Go Far. That has got a change in velocity of 20, and it took it 4 seconds to do it. 20 divided by 4 is 5, and I've made a mistake over here. What should that be? That should be 3. So my bad. Meters per second squared. And, well, this is part of our justification, but are they right? Manufacturers of Go Far claim that theirs have the greatest acceleration, and this one was Go Far, and yep, it has got the greatest acceleration. So here we get 1 mark for making these calculations. So we need to make a calculation with using this. If we make a calculation using that, then we get 1 mark, and we get another mark for all of these calculations being correct. Okay, so I would have actually lost a mark there, my little mistake there, but I'm sure you managed to get all of these correct for 2 marks. And we need to, next part of what we need to do, we need to calculate the kinetic energy. Okay, so kinetic energy is equal to half times the mass times an object's velocity. So we do a half times what we're finding the kinetic energy of the go far. The mass is 600, and we're looking for its velocity at top speed. So its top speed was 20, but whoops, velocity squared there. So it's going to be 20 squared. So let's work this out. So we've got half times 6, and then instead of writing this as 20 squared, let's write it as 400, which is the same as 20 squared. And when we work this out, we get an answer of 120,000 joules there. So 1 mark for making that calculation. Okay, next one, we are sliding a shoe down a ramp and measuring the time in seconds, and we're changing the size of the shoe and measuring the time it takes to go down the ramp. And we're being asked, what conclusions can we make from this data? Now, there's a couple of ways that you can go about answering this question. Well, what the main conclusion that we need to say is that the larger the shoe, the longer it takes. Okay, so the average time here is for the large shoe is a lot larger than the average time for the small shoe. Okay, so if we've stated a conclusion, then we get 1 mark. But we need to justify our answer, so that's where that other mark is. So we could have said for our justification, we could have said that a larger shoe is bigger, so there'll be more friction. Or another way you could have gone about this is use the table to justify it. Okay, so option 1 would be to write something like, the conclusion is the larger the shoe, the longer the time, because a larger shoe has a larger surface area and therefore more friction. That's one way you could have gone about it. Or the conclusion is that the larger the shoe, the longer the time, and I can tell this because the size 9 shoe has got higher values than the size 5 shoes. So you're being asked to either use some science or interpret a table. Next question. Linked in with the last one, another student tries to make the same measurements with another ramp and a shoe of size 4. The key bit here is that they're using another ramp. Right? It's not a fair test if they're using another ramp and a shoe of size 4. So what did we have before? Before we had it going up to size 5. Now we're trying it with the size 4. And something we should notice is this, if we work this out, then we get an average of 1.3 seconds to go down. Now our averages over here, what are our averages over here? We have an average of, so that'd be 1, so that'd be an average of 0.9 there, and here we've got an average of 1.2 there, and here we've got an average of, that would be an average of about 1.3. Let's compare that with our average over here. Well, this average for the size 4 shoe is more like the average for the size 9 shoe there. So it's saying here, you must have made a mistake. Your results don't fit the data. So is he correct? Well, I think he is correct. So he is correct. I think a mistake's been made. But again, we need to justify our answer. So two ways that we could have gone about this. So we could have identified that another ramp. Okay, so identified that the ramp is different. Then that's one idea. We could have also pointed out that the results could have been affected by like different reaction time. So another student might have different reaction times. Okay, so we could put here reaction time. And also, another way we could have gone about it is that we could have compared the data. So we could have said that size 4 shoe has got a similar average to the size 9 shoe. That's one mark. We could also have said that the time differences are small. So if we take a look at our time differences, then our time difference between the here and here, we're measuring at about 1.2 seconds to the nearest 0.1 seconds. So there's quite a large margin for error. So we could say that they're small times. So there's going to be a large error. And that's one point that we could have made there. So what do we get a mark for here? So we get a mark for, so we get 1 mark for each of the points that we've made. So we could have either said the ramps are different, the shoes are different, or we could have said the results don't fit the table. We could have also said the sample size is small, the time differences are small, and the slide time depends on other factors. And that's what the marks that we get for that one. Next one, and this is quite a difficult one. So we're talking about the forces on the shoe as it moves down the slope, and what do we need to do? We need to complete the sentence. The pair force of the friction from the surface on the shoe is, so the pair force of the friction on this pair force of the friction from the surface of the shoe is friction from the shoe on the surface. So whenever we have an interaction pair, one thing has a force on the other. So here we've got the force of the surface on the shoe, and then the pair force of that is the force of the shoe on the surface. Here we've got this part, the second part. So we get 1 mark if we got that bit right. And the pair force of the weight of the shoe is, and this is quite a difficult one. So the thing that's causing the weight of the shoe is gravity, and gravity is caused by the mass of the Earth. So the mass of the Earth pulls the shoe, and the pair force is the shoe pulling on the Earth. Okay, so 2 very, very difficult marks there. So you did very well if you got both of those there. Next question. Describe the resultant force of the shoe as it starts to move down the slope. So for this, we're going to refer back to our diagram. And this diagram here, so we've got all sorts of different forces, but we need to know the overall force, the resultant force. The resultant force is going to push the shoe in the direction that it's going. So the resultant force is going to be in the direction that it's going. What direction is the overall force going to be? Well, it's going to be moving in this direction. So it's going to be moving down the ramp. Okay, so this is the overall force. Even though there's all these other forces, the overall force, the resultant force, is going to be pulling down the ramp. Okay, so in our answer here, describe the resultant force in the shoe, it's going to be pushing down the ramp. Next question we need to do is Ross measured the time that it takes for the shoe to go down the slope, the weight of the shoe, and the mass of the shoe. And what we need to do is say which quantities does he have to work out, which quantities does he use to work out each calculated value. So the average speed, to calculate the speed of something, we need to know the time, and we need to know the distance that it's gone. In this case, the distance is the length down the slope. So to calculate speed, we need the time and distance down the slope. The average vertical velocity, so in other words, how quickly is it moving either up or down? Like it's moving kind of along at a diagonal, but at every point it's moving down. So to do that, average vertical velocity, we need the height, the vertical height, and we need the time. Take those two quantities and we can find the average vertical velocity. So changing gravitational potential energy when the shoe slides down the slope. So when we're talking about changing gravitational potential energy, we're talking about the weight of the shoe times the height of the slope. And I will also give you a mark if you have done the weight of the shoe and the mass of the shoe, because we're going to assume that the weight and the mass they don't change. So the mass of something is always constant, and its weight changes depending on what sort of gravitational field it's in. And in this case, we're always in the Earth's gravitational field, so the weight of the shoe is going to be the same as the mass. And we also need to find the average momentum of the slope of the shoe as it goes down the slope. Well, for momentum, we need to know the velocity of something and the mass of something. So to find the average momentum, we need to find the mass. And to find the velocity of something, we need to know the distance that it goes, the length of the slope, and the time taken. And what we get marks for here is we get marks for each correct row. So if you've done a correct row, then give yourself a mark. As the shoe moves down the slope, it speeds up. On the axes below, sketch the shape of the velocity time graph. Sketch the shape of the velocity time graph. So we get a mark here for it starting here. So if your line starts from there, then you get a mark. And we also get a mark for any kind of positive gradient. So if your line does that, then that's fine. If your line does that, then that's fine. No, that's not a positive gradient. If your line does that, then that's fine. If your line is, let's just get rid of those quickly. If your line is more of a kind of curved line, so it's going curved like that, then that's fine. If your line is like that, so curving upwards a little bit, something like this, then that is absolutely fine. One mark for it starting here, and one mark for a positive gradient. And again, for these 6 mark answers, I'm just going to invite you to pause the video and assess this one in a good amount of detail in your own time. So pause the video. Okay, next one. What are we looking at? We are dropping some paper cases through the air, and we're seeing what sort of speed they fall at, and we're taking some measurements with regards to the speed that they're falling at. And first thing we need to do is we need to complete 2 gaps in the table. So we need to find, what have we got here? We've got the height that it's dropped from, time that it falls, and the speed that it's is being calculated here. So to work out the speed, it's going to be the height divided by the time, and what we should get here is 0.510 meters per second. And average speed, well, we need to find the average of these, and we get 0.505 there. Next question. Use the table of data to comment on Jim's idea that the cake cases fall at a steady speed. Now, do they fall at a steady speed? Well, let's take a look. Here, in these three, we're dropping it from 1 meter, and in these ones, we're dropping it from 0.5 meters. And here's our average for one, and here's our average for another. And it's clear that here, this is a lot smaller average speed than here. So was Jim correct with his idea? Well, no, he wasn't correct with his idea. He said it falls at a steady speed, and these are different speeds. So what could we get marks for here? We could either say that Jim must be wrong, because increasing the height increases the speed, which doesn't indicate a steady speed. Or we could say, we could discuss the like the averages. So we can say that the or we could go the other way and say Jim is right. They fall at a steady speed because their averages are inside each other's ranges. Okay, so this average here fits inside the range here. So the range in here is what we got. So our lowest one is 0.467, and our highest one is 0.510, and the average for here, it fits in between here. And our range here, our lowest one is 0.488, and our highest one is 0.526, and then this one, it fits in there. So if you've given an answer something like that, then that's another mark there. And finally, for each height, Jim measures the time for it to fall more than once. The measurements are not the same. Why aren't these measurements the same? And there's a whole range of answers that you could have, and if you've got two of them, then you get two of those marks. So you could have mentioned about any drafts or air current or wind affecting it. You could have mentioned the air temperature and pressure could have affected it. You could have mentioned each time a repeat is taken, the cases could have been released in a different way. You could have mentioned that the shape of the cake case might change. So in other words, each time you do a test, it might change shape. You might crumple it a little bit. You could have mentioned that there are really, really short times. So it's difficult to get the same result over and over again, to get those timings perfect. And the cake case does not always travel down. So that's the final idea. So the idea that it may not travel completely vertically down. Moving on. And again, your last 6-mark question in this paper. And again, I'm going to get you to pause the video and mark your work. And our next question is going to be about a car. So let's have a quick look at this. So car, there's the mass, 800 kilograms, there's the velocity. When we've got mass and velocity, that hints to me that we might be doing something to do with momentum. Okay, something to do with momentum here. So it turns out that our first question isn't about momentum. It is in fact to do with the braking force. Okay, so we need to calculate the braking force needed to stop it. Now, to find the force of something, we need to do the change in momentum. So it turns out we did need to find change in momentum divided by the time, and that would have given us change momentum is, well, our momentum is the mass times the velocity. Our momentum here is 800 times 50, and then that gives us, what does that give us? 1,000, no, 12,000. So that's our change in momentum. If you got that far, then you've earned yourself 1 mark. But to get the 2 marks, we needed to then take our 12,000 and then divide it by the time, which is hidden there, it's 2 seconds, and then that gives us 6,000. So answer here, 6,000 going there. Next part. And we need to, next one, so it's a linking up one. So remember, just like when we're ticking boxes, don't do things unless you're sure. You're going to have a pencil in your exams and things, so do them in pencil first, because otherwise what you'll end up happening is you might say, oh well, it's that one, and that one. Oh no, made a mistake there, I changed my mind, it's not that one, actually that one, and that one's not that one. That one is this one. So what we're trying to avoid is, say your work is looking like this. I don't know, I don't think it's clear that the you know what you're doing there. So we're going to get rid of all those, and let's draw some proper lines on there. So we get that one, and that one, and that one. And let's see what we get marks for here. So if we've got 3 correct, so all 3, that gives us 2 marks. And if we've got 2 correct, and then that gives us 1 mark. And if we've got 1 correct, then that gives us 1 mark. And if we've got none correct, then that gives us no marks. Let's take a look here. So this one's a little bit tricky. And again, let's work through our options. So we have to put a tick next to the correct relationship, and we're looking at these forces. So let's take a look at this one first. So B minus C equals A. So what that's saying is, if you take the downward force of the car and the upward force of the wheels, then that will give you the frictional force, which doesn't quite make sense to me, so not too sure about that one. The E, so the downward force coming down, is take away 4 lots of this. So this force represents one of the forces on the wheel, upwards forces on the wheel, and there's 4 wheels of the car. So the force up minus the force down equals 0. So it could be that one. Let's not tick it yet. Let's be sure. And this one is saying that B plus C equals A. So this force pushing up plus this one is the same as this one. That doesn't make sense to me. And then if you take all of these forces together, this one plus this one plus this one, or rather the force of friction plus the downward force plus the upward force is equal to 0. Well, it's not that one either. So let's give me that one. Next question. Here are 4 possible displacement time graphs for the car as it slows down, and we're looking for the correct one. And I'm pretty sure most of us have probably gone for option B there. And the reason that we're doing this is we have interpreted this as a velocity time graph. And as a car slows down, that is the shape of its velocity time graph. It starts off with a high velocity, and over time its velocity goes down. But we're looking at a displacement time graph here. And so our displacement time graph is saying how far it goes and in what time. So here, what this is saying is that our displacement increases. So in other words, distance we travel is increasing over time, but it's increasing at a constant rate and then all of a sudden stops. This one here is saying that our displacement, so it's moving along, but it's moving along at a slower rate. And then this is saying that, well, it's starting at the top and it's going down, so it's going backwards. So it's not B, it's in fact A. Next question. So Jill throws the ball up in the air and catches it on the way down, and the answer that we were looking for is that one, and we get a mark for that one. When Jill catches the ball, she allows her hand to move down with the ball. Explain the effect of this action it has on the impact force of her hand. So, we need to talk about the force. So we need to say it had a smaller impact force, but we also need to give an explanation, so it needs a reason that it has a smaller impact force because, and these are the options that we could have had, the time taken for the ball is increased, time taken to stop is increased. That's one of the ways we could justify it. Or we could have said increased time for the ball to change momentum, or increases time that the force acts, or increases the time for the ball to slow. Any sort of mention of increasing in time for it to slow down. And that is it. If you've got any questions about this, then just drop me an email here at a.preston-manor.com, and let's put that into a decent size so you can see the whole of it there. So, any questions about it, drop me an email.